So our next speaker is Harry Foster, who's at Siemens EDA, and he's in the States, so he's doing a remote presentation for us. He's a chief scientist in verification for Siemens Digital Industries Software, and is the co-founder and executive editor for the Verification Academy. Harry served as the 2021 DAC General Chair. He holds multiple patents and has co-authored 6 books on verification. He is also the recipient of the Accelera Technical Excellence Award. Hi, Harry.
Hello.
We can hear you. Go ahead.
Okay, it's a thrill to be back. It's a thrill to present at Verification Futures. If I recall, Mike, I think I participated in the original one back in 2011. I certainly have participated in multiple ones over the years. Unfortunately, I can't be there today. My dad has his 90th birthday. My parents, their 70th wedding anniversary going on at the same time. So I decided to do this remotely. But again, I'm thrilled to be back. The title of my talk is 3 Pillars of Intent, Focus, Insight. Really, my goal today is to initiate an ongoing discussion on the need to change the way that we philosophically think about design. So let me move this down and see if I can get this to cooperate. There we go. So I've organized my talk into 3 sections. One is the crisis, the second, the problem, and the third is the prescription. And I hope I'm not sounding overly melodramatic, but I do claim that we are in a crisis, and I will quantify that on the next set of slides. So we've seen this before many times. I'm going to do a slightly different spin on it. In the late 1990s, Semitech basically set off an alarm, what was referred to as a design productivity gap. Essentially, what this was is that we could manufacture more transistors and we'd actually had time to design, use a leverage essentially in design. In other words, manufacturing productivity gains were growing at a 40% CAGR, while design productivity gains were growing only at a 20% CAGR. Now we solved this, or at least we, you could say, or you sink or swim. We were treading water and solved this in the sense that with the adoption of reuse methodologies, the emergence of an IP economy in terms of design, and certainly improvements in EDA, helped address this gap that was growing. But the bigger concern, and a lot of us have been screaming about this for years, a more ominous gap is what we refer to as the verification productivity gap. And I maintain that this will not be solved by reuse methodologies. And we'll get incremental improvements in terms of verification technologies and stuff. I maintain that to solve this problem is going to take a philosophical change in the way that we think about design. And that's really the theme of my talk today. Now I'm going to quantify this gap, this crisis, with a couple slides. And sure, many of you have seen this particular slide, which comes from my biannual study on functional verification. But I'm going to present this a little bit different today. As we see here, consistently 1/3 of projects are able to achieve first silicon success. But if you look closer at the cost impact in terms of wafers and mask costs, this is a concern. The cost multiplier by feature size with respect to 28 nanometers, let's look at that. The wafer cost at 3 nanometers is 10 times the cost at 28 nanometers. And the mask cost at 3 nanometers is 25 times the cost at 28 nanometers. So even though the respin rate has stayed constant, and we've seen it's been roughly 1/3 going all the way back to 2002, the cost has not. Okay, so that's one data point. And let me click this. Another data point is in terms of just growing expense, as I think everybody's talked about this today. This is the IBS report from last summer. Their new report is due out next month. I'm not anticipating significant change. Generally, that's the case on this particular data. Now, I'm only focusing on, in this slide, the verification, validation, and software costs. And what we see is that at 3 nanometers, the verification validation cost is 11 times more than at 28 nanometers. The software development cost is 14 times more than 28 nanometers. And obviously, software has a direct impact in the overall verification validation cost. Okay, so that's another data point in my claim about the crisis. And then the next thing we'll talk about is actually growing complexity. And I think this slide is telling, it's reflective of growing complexity. It appears worse on FPGA projects in terms of their success. Here we see that only 17% of FPGA projects are able to go into production without a non-trivial bug escape. And as you know, certain market segments, this is pretty significant. Mil-Aero is a classic example where you think, oh, it's just an FPGA, I can go upgrade the FPGA. That's not true when you take a cover off a plane and then you got to revalidate the entire system. So the cost can be enormous. But this is just another indication of growing complexity, the lack of success here. And then the other data point I want to look at relates to logical, basically, what was contributing to flaws. This slide's interesting in that we see, a little over 50% of all respins are due to logical function. That's the largest category. But what's actually encouraging on this slide to me is notice this decline in clocking, from clocking issues. This is due to the industry, the ASIC industry, I should say, maturing and adopting these clock domain crossing solutions. Now, I'm not showing the data here, but if you look at FPGAs, it's the opposite because they have not adopted these clock domain clocking solutions. They're actually seeing an increase in clocking issues. The other interesting thing to take away from this, notice this spike in terms of analog. And what's going on here? By the way, I put together a panel about 1.5 years ago to discuss this, and this is industry experts. And one of the key takeaways in this is that there is a lot more analog being integrated on ICs today than there used to be. And it doesn't matter what geometry size. It's not, this problem is not limited to the latest and greatest 7 or 5 nanometer or so on. It's across the board. So there's a lot more analog. And then I've maintained for a while the other contributing factor to growing complexity is the increased amount or increased number of requirements that we have to deal with today. That's reflected on this. If you look over on the right, for the first time, we started tracking safety and security. But anyway, so we have power, clocking, safety, security, software. There's just a huge amount of requirements that we have to deal with. And that exploding aspect is contributing to the growing complexity. So if we look at the impact of this, and again, many of you have seen this slide, which I've tracked for many years. This tracks the mean peak number of engineers. So since 2007, design engineers increased by 32%, which is actually remarkable if you think about it in the sense that, we've gone through multiple iterations of Moore's Law during that period. Verification engineers have increased by an amazing 138%. So again, another data point, this is increasing the cost of verification, the fact that we're having to grow the teams in terms of verification engineers. And then the final data point is still only 2/3 of projects are able to achieve their schedule. Now, obviously, the schedule is another thing that increases costs. And again, I hope I'm not sounding overly melodramatic, but I make a bold claim. We are in a verification crisis. Okay, so my next section, I'm going to focus on a little bit more detail on the problem. And, oops, It's stuck. Oh, here we go. I got it. Okay. So I'm going to go back in time again to the 1990s when we started seeing the emergence of verification genes. Now, I used to joke that I always wanted to write an article called "Was Divorce the Right Answer?" because there were some good things, but also some bad things that occurred in this process. Now, we needed to move to the separation of teams for a couple of reasons. One was to ensure an independent interpretation of the spec, and this enabled us to flush out bugs just in the process itself, identify misunderstandings of the spec. The second thing that was occurring, and it certainly has gotten worse over time, I maintain, is the increased complexity of verification environments, and this required unique engineering skill. Now, the problem is, on the extreme case, and again, I say this is the extreme case, we see that design was thrown over the wall and it became a verification problem. In fact, there is still today a fallacy, even when they're not thrown over the wall, there's a fallacy that quality can be verified into a product, and that's just not true. And the way I'm going to justify that claim is through this. So this is W. Edwards Deming, Dr. Demings, and he's known as the father of statistical processes. He went into Japan after World War II and totally revolutionized their manufacturing capabilities, where Japan went from some of the worst quality products to some of the better, best, and that certainly you can think in the mid 80s in terms of automotive, they were leading in terms of quality at that point in time. He wrote a book in 1985, and some of you might be familiar with this. The book was called Out of the Crisis. And Deming made the point that quality cannot be inspected into a product. It must be built into the product. And to demonstrate this, he conducted a number of management training courses, exercises. One was that he filled 2 boxes with white beads, sprinkled a handful of red beads into the box representing bugs, and then divided the class into 2 groups. He gave each group a wooden box and a paddle to remove the red beads. Now, his plan was to reward one group who removed the most beads and then penalize the other. After the exercise, what's interesting is that he gathered the groups together and had them present what they learned. And the groups focused predominantly on the techniques for removing the red beads that they had developed. Demings then told them that they totally missed the point. It didn't matter if you reward or punish a group, the red beads remain. So his solution to the problem is not to find the optimal solution for removing the red beads. The solution is not to put the red beads in the wooden box in the first place. And I maintain this wisdom is applicable to IC design today. So on this slide, I'm going to talk about cost multipliers. By the way, I was involved in an analysis recently of root causes of various bugs. And there was this one high-performance computing project that experienced a bug. By the way, and these bugs are beyond just complex corner case bugs escaping in production. There were many many trivial bugs that were escaping in production. And again, this one case where a high-performance computing project experienced a respin even after billions of cycles of constrained random simulation followed by directed testing. And upon closer analysis of the problem, it was revealed that the respin could have been prevented if the engineer had only ran lint before he checked in the code. It was missed. It was a trivial bug, missed after all this simulation. Now, granted, this is an extreme case, an outlier. But even if he had found the bug before they taped out, you still have the extra costs associated with debugging, triage, design, synthesis, followed by additional verification. So the cost is significant the farther along you get in the process. And I illustrate this. This was in discussion with multiple managers involved in 5 nanometer ASICs. These are estimates. Whether they're exactly accurate is not really the point. Certainly at different geometries, you're going to have different cost multipliers. The reality is there is a cost multiplier associated with finding a bug later in the design phase. So, for example, if I find a bug during the IP verification phase, it's 8 times the cost of what if I had found it before I had passed it on the verification in the development phase. And obviously, this has an impact on the overall project in that we basically have 3 knobs that we can turn to adjust the project, and that's resources, scope, and schedule. And we've already seen the schedule impact of this in terms of bugs and the data presented. So let me move to what I call the prescription. So bugs obviously occur, in all over the project, from architectural to the implementation, synthesis, and so on. I don't know why it seems to be holding up. Here we go. So to reduce costs, though, we need to improve the RTL quality while reducing bug density within the design. And this is an idea that I have. In other words, we need to reduce costs by finding and fixing bugs, and we need methodologies that enable us to do this. By the way, there have been some that have emerged, like test early and often combined with continuous integration. But I maintain we need to focus more on the design process itself. And this introduces the idea of what I call intent focus insight as part of the design process. And we'll talk a little bit more about that. Now, this is an abstract view. I could have shaped these curves many different ways. But the idea I'm trying to convey is the importance of reducing bug density at later phases of the development cycle. Now, sure, it's a shift left approach, but I maintain it's something bigger. It requires a philosophical change in the way we think about design. And again, I call this intent focus insight. We want to certainly clean out those trivial bugs before they are found later in stage, or even in silicon, like I discussed in that high performance computing project. So and by the way, in a project that incorporates a design plus intent methodology, that it doesn't necessarily make verification any less important. The goal, again, is to improve verification efficiency by reducing debug bug density. And on this slide, I'm showing what I call the 3 pillars of this process. One is the produce, and that's the produce correct by construction. The prove, and that's to prove the intent is met. And then the protect, which is protect intent throughout the development lifecycle. Now, there's many different ways in the produce that we can improve that process. And I'm picking on this approach here. This is the adoption of high-level synthesis when we can. Now, why is this important? Well, by the way, I've had a number of engineers ask me, do some languages lend themselves to more bugs than others? And the answer is no. In fact, this has been studied across multiple software projects. And I've actually studied this data in my own, the studies that I do every 2 years. I've gone and look at language and see if one lends itself to more bugs. The answer is no. There is a observed rate, a bug density rate that has been quantified in the software world, and it's actually true in the hardware RTL world. That's the number of bugs per 1,000 lines of code. In fact, I have a colleague of mine who's a manager in a company in Austin. This is something he tracks very closely. So we find that typically between 15 to 50 bugs for 1,000 lines of code. By the way, the variance in that depends on the complexity in terms of the concurrency of the code. Nonetheless, again, we should expect roughly 15 to 50 bugs per 1,000 line of code. Now, when we move up to high-level languages and high-level synthesis, we reduce the amount of code. For example, you might have a case where 100 lines of high-level language is equivalent to 1,000 lines of RTL. We should expect a 10x reduction in the average number of bugs. So we have 1 to 5 bugs of high-level language design versus 15 to 50 bugs of the equivalent RTL design. So this in itself reduces bug density later in later stages of the design. So wherever we can, we should apply high-level synthesis and high-level languages. We can't do it everywhere. So another key component of the produce pillar is we need HDL design environments that integrate deep analysis capabilities into the creation process. And therefore, we can quickly assess new and reuse code quality to prevent bugs during development. The other advantage, by the way, of high-level synthesis is that we actually speed up simulation significantly, as I show on this slide. Okay, so this, by the way, this is the only marketing slide I have, but it illustrates the range of static solutions that can be adopted during design. And again, I'm emphasizing design. We need to improve design. And so I went through the different pillars here. You know, the first pillar was the produced designs that are correct by construction. The second was proven designs meet the design intent and quality objectives. And then the protect phase, where we want to ensure that we continue, we're not introducing new bugs along the way. So I talked about the produce a minute ago. The prove. This, you can see there is a whole lineup of solutions that are targeted at designers, such as RTL linting, advanced RTL sequential linting, X sensitivity checks, clocking domain reset, and so on. There are a lot that have emerged over the years. In the protect function, this is continuous integration becomes important here, and this is where automatic static solutions help too, because they can be built into this continuous integration process and finding bugs as the design is changing, in the sense that we're integrating multiple blocks. We might have misunderstanding in the way the interfaces work and so on. Another key component of this is the basically we need to be checking for network netlist-based CDC issues during this particular period. Okay, so the point is leveraging automation during the design process. We're reducing bugs and so on. So to wrap this thing up, my goal today, again, was to start a dialogue in our community concerning finding a path out of the verification crisis. And I maintain that it requires a philosophical change in the way we approach design, with a foundation built on bug prevention. And one solution that is readily available today is focusing on intent-focused insight during the design phase. And there's a lot of solutions that we talked about there. By the way, I wrote a paper on this that goes into a lot more detail than I have today. I titled this Out of the Verification Crisis. You can see I borrowed the title from Deming. With that, I am done.
Okay. Thank you very much, Harry. That was a fascinating talk as always, and we thank you for your time and for presenting from the States. And we're going to have to go straight into our break now because we're a little bit behind schedule. But thank you anyway, Harry. Thank you.
Thank you.